Hello everybody, in this lecture we will be solving 1981 IMO problem number 6. Here is a view of this functional equation problem. Our function f of xy, accepting two parameters x and y, satisfy these three conditions for non-negative integers x and y, and we would like to determine a particular value of f. To begin with, like in any other functional equation problem, we try to see some patterns by substituting different values into our function. Let's start by substituting in the first equation. Substitute y equals 0, and we will get f of 0, 0 equal to 0 plus 1, 1. Again, probably in the first one, substituting y equals 1, f of 0, 1 would simply be 1 plus 1 equals 2. And for example, now moving on to the second equation, plugging in x equals 0, f of 1, 0 is simply equal to f of 0, 1, but we already got f of 0, 1 as 2. That's nice. Then I can continue. Consider the third expression and plug in x equals 0 and say y equals 0 into that one to get f of 1, 1 is simply equal to f of 0, f of 1, 0. So that's 2, 1, 0. And now we can use the first expression here using number 1. We would get that because it starts with a 0 component for the x, that's simply 2 plus 1, which is simply equal to 3. And in a similar way, so for instance, if we continue in this fashion, so I'm interested in expression 3 here, plug in x equals 0 and y equals 1, then we'll get f of 1, 2, yeah, that's more reasonable. That is simply equal to f of 0, f of 1, 1, right. Now we can go back to this principle, to the first principle, and substitute with f of 1, 1 plus 1, but f of 1, 1 we just got it as 3, so 3 plus 1 equals 4 for f of 1, 2. This gets us thinking actually. Now a pattern started to emerge. That's the first pattern we have so far. If you look at the ones where the first component is a 1, f of 1, 0 is 2, f of 1, 1 is 3, f of 1, 2 is 4. That gets us thinking that we might have something going on in here. So I claim f of 1y is simply is just 2 more than, so y plus 2. Right. And we have already verified it for at least 3 different values, and it looks reasonable. So let's use induction to prove it. So the base case, we have at least several base cases already proven. So let's assume that the induction step that this result holds for f of 1y minus 1 is equal to y minus 1 plus 2, which is simply y plus 1. And let's try to see if we can get this result. So f of 1y, that is simply using the last one here, number 3, the third property here, f of 1 y, substitute x with 0 and y with y minus 1, x with 0 and f of 0, f of 1, and then this one would be y minus 1. Alright, but we have from the or let's split it in 2 steps. Recall from property 1 that this is just y plus 1, y plus 1, right? So whatever is in here plus 1, here plus 1, so this is f of 1 y minus 1 plus 1, and now f of 1 y minus 1 was just y plus 1, so so that's simply equal to y plus 1 plus 1, which is y plus 2, as we wanted to show. Okay, going back to searching some further patterns, in a similar way we can so we already discovered the pattern for the, if you will, layer 1. Now we can try to see if we can find a pattern for layer 2. So let's start with f of 2, 0, if you will. So f of 2, 0 is just, for example, using this one, the second property, replacing x with a 1. So that's simply f of 1, 1. But f of 1, 1 earlier we have it as 3. Now let's investigate further the first component for being 2, and let's continue and see how far we can take this argument. In this case, I will be using the third one, replace x with 1 and then y with 0, x with 1, y with 0, f of 1, and so f of 2, y we took it as 0, f of 2, 0. That's simply equal to, and at this step, right, f of 2, 0 was 3, so that's simply f of 1, 3, but we already know that f of 1, 3 is equal to, I think, oh yeah, of course, I do have my claim, right? So that's simply 3 plus 2, which is 5. Similarly, we can now proceed as f of 1, f of, and the third property again, 2, 1, but that's simply f of 1, f of 2, 1, we just got it as 5, and finally, recall from our claim earlier that this is just 5 plus 2, which is 7. And so on. So therefore, again, we can come up with an induction, with a claim which we can prove by induction. So I claim that if you look at this relationship, 3, 5, 7, and so on, so we believe it will continue in this fashion, it's fair to claim that f of 2y is simply equal to, yeah, we keep adding 2, so there's a 2y there. Plus 3 because f of 0 is 3, yes. And that should be fairly straightforward using induction again, so I'll leave it to you as an exercise as well. Proof, induction again. So we have already proven some base cases here. So the induction step, you assume, let f of 2y minus 1 be equal to 2y minus 1 plus 3, which is 2y minus 2 plus 1. And now we can substitute back into the thing, so let's just finish it as we started. F of 2y, which is simply equal to f of 1, f of 2, right, so 2 y minus 1, but recall f of 2y minus 1 was 2y, so f of 1, 2y plus 1, and finally f of 1 of something was just, by this definition, you just add 2 to the other guy, 2y plus 1 plus 2, which is 2y plus 3, and this confirms the claim. So our claim is sustained. So far I was able to advance and prove my claim for the first level. I have it for the second layer. Now we can go on to the third layer. So after working a few steps, we can probably come up with a claim. So let's start with f of 3, 0, which is simply equal to f of, right, if you use this definition again, so f of 3, 0 would be f of 2, comma, is there an easier way? Right. So we can use the second result directly, right? So therefore f of 3, 0 is just substituting 2 into it. So this is f of 2, 1. That makes sense. F of 2, 1. But earlier we got f of 2, 1 is just 5. That's a 5. And let's go to f of 3, 1. Well, f of 3, 1, now let's use the third definition, the third rule, f of 3, 1, so substitute x with 2 and y with 0, x with 2, y with 0, so I will f of x, 2, y with 0, so therefore f of 3, 0, yeah, f of 3, 0 here, f of 3, 0 here. F of 3, 0 I already got as 5, so f of 2, 5, and f of 2 something is given by this formula, which is 2 times 5 plus 3, which is 13. And so far I'm not able to see a pattern emerge, so I'll keep going until I see the pattern emerging. So that's a 2 f of 3 1, which is f of 3 1, we just got it as 13, and now f of 2 13 is just 2 times 13 plus 3, 2 times 13 plus 3, which is 26 29. Okay, I still don't see anything. Let's keep doing until we can see something. Oh, I'm high. I was taken by the moment, huh? So that's a 3 3, and as a result we have a 3 2 here, but we previously calculated 3 2 as 29, and that's simply f of, right, so it is just 2y, so 2 times 29 plus 3, 58 61. Oh, so what is the pattern that emerges? So this one is 16 minus 3. This one is 36 minus 7. 64 minus 3. Right. So, okay, so if you pause the video like I did and tested out a few cases, you just come out with the following result. So if you start with 3 0, oh, I forgot about this one obviously. If you start with 3 0, that's just right. So you have 2 cubed minus 3. This one is 2 to the 4th power minus 3, 16 minus 3. This one is 2 to the 5th power minus 3. Yeah. That's the one that's working. So therefore I can make my third claim in a row, this time for the third layer. I'm almost done. I have just one layer left. I claim this is just equal to 2 to the power, starting with, for 0 we started with, so that's 3 y plus 3, and then minus 3. So we have this claim, which again very easily you can prove by induction. Prove it by induction. I'll just leave it to you as a simple exercise. So now we are to find the pattern for the 4th layer. So f of 4 0, like we did in the previous questions numerously, because 4 0 we will make use of this. We will start with the second condition and then we will move on to the third condition. So f of 4 0, replacing x with 3, is equal to f of 3 1. F of 3 1, but f of 3 1 earlier we have it as 13. F of 4 1, that's just, now we can use the third line, so that's just f of 3, f of 4 0, I think, one less, yes, so it's one less, y 4 0, but this is just f of 3. F of 4 0 in the previous step we got it as 13. Now f of 3 13, if you remember the rule that I didn't even bother proving, if you just substitute 13 into this thing, it's 2 to the power 13 plus 3 minus 3, which is 2 to the power 16 minus 3. I won't even bother trying to calculate this result. In a similar way, I can calculate f of 4 2, which is f of 3, f of 4 1. But this is just f of 3. 4 1 was just this ugly number. And now for the first time, f of, well, okay, so let's finish this. F of 3, 2 to, so this thing is 2 to the power, so replace y, which is our y here, with this y plus 3, so 2 to the power 16 minus 3 plus 3, and minus 3, which is just 2 to the power 16 minus 3. You can try higher and higher values until you see the pattern emerge. So f of 3, f of 4 2, but that's just f of 3. 4 2 was this ugly expression. 2 to the 2 to the 16 minus 3, that's equal to right, so the rule was for the previous one was this, so all we care is the third component, and we will add 3, so 2 to the power 2 to the power 2 to the power 16 minus 3 plus 3 and minus 3. These 3 cancels out. Okay, so here emerges the thing. So 13, right, so let's just write it. So this is just 2 to the power 2 to the power 2 square, minus 3, right. This one is simply 2 to the power, so 16 can be replaced with 2 square because that's 4, that's 2 to the power 4 is 16, and there, boom. And not surprisingly, of course, this is just 2, and then 16 is just 2, 2, 2. We have 4 2's, and including the base, 5 2's minus 3. Of course, this is just 2 to the power 2, 2, 2, 2, 2 minus 3. Aha! So I nailed it, right? So we have the desired result, which is, in general, this is simply a tower of 2's. So I need to be careful on counting the 2's. So how many 2's here? So when y is 0, we have 3. When y is 1, we have 4 2's. Of course, when y is y, we have y plus 3 2's, followed by minus 3. So therefore, so we have f of 4 1981, which is just 2 to the power, you have a power of 2's, and then minus 3, where in this power of 2's, how many 2's do we have here? Is right, so 3 more than the, so 3 more, so where we have a tower of 1984 2's, and that solves the problem. Hope you guys enjoyed it, and looking forward to see you guys in our next lecture.